So let us continue with our study of portfolio of two assets. But instead of considering one safe asset and one risky asset, let us now consider what happens when you have got a portfolio consisting of both the assets which are risky. Okay, so just to make things more concrete, imagine that you have got two assets. Let's call them asset D and asset E. So D stands for, you can imagine, debt fund, and E stands for equity fund. And suppose we are given the following parametric values, that the expected rate of return from the equity asset is 13%. The expected rate of return from the debt asset is 8%. The standard deviation of the rate of return of the equity asset is 20%. The standard deviation of the debt is 8%. The covariance is 0.0072, and the correlation coefficient is 0.30. Notice that you don't actually require both these pieces of information. Any one of them would have been sufficient based on the other things you could have calculated directly, right? So for example, suppose I did not give you rho DE is 0.30, but I had given you this information. So you could have combined this along with sigma E, sigma D to calculate rho DE directly, right? Okay. Let WD be the weight of the debt asset in the portfolio and WE be the weight of the equity in the portfolio. So clearly the WE and WD are linked by the fact that WD plus WE has to add up to 1, because these are the only two assets that are possible in the portfolio. So we can define the rate of return on this portfolio. So let's call that RP. So that's the weighted average of the rate of returns of these two assets, where the weights again are given by the weights in the portfolio. So the expected rate of return is the weighted average of the expected rate of return of this assets, with the weights being equal to the weights of the portfolio. However, the variance is not the weighted average, right? So we looked at the formula for the variance in the previous lecture, and we had found that sigma square P is given by W square D, sigma square D, plus W square E, sigma square E, plus 2 times WD WE multiplied by sigma TE. So this is in terms of covariance. We could have also alternatively written this formula down in terms of correlation coefficient. And this is the expression that we would end up getting by substituting sigma DE to be equal to rho DE multiplied by sigma D into sigma E, right? Okay, so the second expression that we have here, the one involving correlation coefficient, is useful to draw a few insights, right? So suppose that we have given the values of sigma D and sigma E, but maybe the values of rho are something that can be varied, okay? So the question is, what's the highest value of variance of the portfolio that you will get based on this? So we can clearly see that the highest value of this expression is going to be the when you have got rho DE is equal to 1. And in that case, sigma square P becomes just the square of WD sigma D plus WE sigma E, right? Why is that the case? Because this term at the end becomes equal to 1. And you can then see that this is nothing but the expansion of the square of this term, right? So what that says is that in this case, when you have got perfectly positively correlated assets, right, then the standard deviation, which is the square root of the sigma square P, becomes the weighted average of the standard deviation of the assets, right? So this is the only case that you have here. However, in all the other cases, when you have got, for example, rho DE to be less than 1, then in that case, the standard deviation of the portfolio is going to be strictly less than the weighted average of the standard deviation of the different assets, right? So that is basically the rationale for stating that the portfolios of less than perfectly correlated assets always offer some degree of diversification benefit, in the sense that by combining the two assets, you can end up getting a standard deviation which is less than the weighted average of the standard deviation of these two assets. What about the other cases? So suppose again we are free to choose the value of rho. How low can the standard deviation of the portfolio become, and for what particular value of rho? So clearly from this expression here, you can see that the lower the value of rho, the lower can be the value of the sigma square P, right? So from here, if we actually see the lowest possible value of rho, we know is -1. So that again represents perfect negative correlation. And if we put rho equal to -1 here, we end up getting an expression which is WD sigma D minus WE sigma E whole square, right? So if we rewrite this in terms of standard deviation, we get that the portfolio standard deviation when rho equal to -1 is equal to the absolute value of WD sigma D minus WE sigma E. Now, this can be made equal to 0, which is the lowest possible value for a standard deviation. Remember that we do not have negative standard deviations, in which case you can actually use that to solve for the weights, because you remember the WE is 1 minus WD. So that's just a linear equation that you can solve for WD. And you end up getting that in that case, WD is going to be equal to sigma E plus sigma D plus sigma E. Okay. And WE, which is 1 minus WD, is given by sigma D divided by sigma D plus sigma E. So you don't have to memorize these formulas. You just need to understand how we can derive these things if you want. Okay, let's get back to our example, which did not have these extreme cases, right? In our example, remember that rho was 0.30, so we cannot use these things that we have studied before, but we can actually solve the problem generally, right? So for example, suppose that we want to figure out that for this value of rho, which is 0.3, what's the smallest value of the variance of the portfolio that we can get, and what would be the corresponding weights? Okay, so in order to answer that, what we need to do is we need to look at the formula for the variance of the portfolio, which is given by this expression. And we can actually convert this into an optimization problem involving one variable by noting that WE is nothing but 1 minus WD, right? So if you put that in and plug in the parameter values that we have given here, we'll end up getting that sigma square P is just a function of WD. And we know how to optimize that. So take the first derivative with respect to WD and set that equal to 0. So if you do that and solve the equation, you will see that you end up getting WD is 0.82 and WE is 0.18. And so this values of the weights of the different assets in the portfolio basically minimizes the variance of the portfolio. Okay. And if you plug this value in 0.82 and 0.18 in this expression here, and as well as use this parametric values, then you can show that this will end up getting to a value of sigma P is equal to 11.45%, right? So we can also see these things graphically. So here what we have is on the y-axis, we have the expected return of the portfolio. And on the x-axis, we have the weight that we are giving to stocks. Now, we could also rewrite the same thing in terms of weight given to bonds, because, for example, a weight of 0 to stocks would correspond to a weight of 1 to bonds. A weight of 1 to stocks is corresponding to a weight of 0 to bonds, and so on, right? So it doesn't matter what you have on the x-axis, weight of stocks or weight of bonds, you just need to be consistent. Okay, so here, let's think about what happens if we have weight of stocks on the x-axis. So for example, if you have a weight of stock of 0, that would mean that all of the portfolio consists of just the debt fund, and hence the expected return is going to be just the expected return of the debt fund, which is 8%. On the other hand, if you have got the weight of stocks equal to 1, then all of the portfolio just consists of this equity fund, and then the expected return of the portfolio is 13%, right? If you choose intermediate values of the weight of stocks, you are going to get some point which is going to lie on this line joining 8% and 13%. And as usual, you can have a value of W greater than 1 or a W less than 0, which would consist of shorting one asset. And you can have, therefore, expected returns being less than 8% or more than 13%. Of course, none of this comes for free. And as you are changing the weights, you are also changing the standard deviation, right? So this is a diagram which looks pretty complicated, but let's go through it step by step. So what do we have? So on the y-axis, we have got the portfolio standard deviation. And on the x-axis, we have got the weight that we are giving to this equity or the stock fund in our portfolio. So what are we doing? We are seeing that as the weights are changing, what is happening to the portfolio standard deviation. Now, what we have done in this graph is that we have drawn this figure for different values of rho. Remember, rho is the correlation coefficient. So the easiest case to consider is that what happens if you have got rho equal to 1. So in that case, remember that we had derived that if you have got rho equal to 1, then the standard deviation is nothing but the weighted average of the standard deviation of the different assets, right? So that would basically just correspond to this line joining the two cases, right? So that is one case. Okay. Um, what happens if you are allowing for different values of rho? So we also looked at what happens if you have got negative rho. So in that case, we can actually go down and have the standard deviation being equal to zero. And you can actually use these numbers to calculate along with this formula that what would those two weights be. Okay. And the other thing that we actually explicitly calculated is that what happens if you have got rho equal to 0.30, right? This is exactly the calculation that we did here. And we showed that the lowest standard deviation that you can get, which would roughly speaking correspond to some point around here, would be around 11.45%. And in fact, we had calculated the weights as well. So the equity weight was 0.18. Okay. So in this case, where you reach the minimum, uh, standard deviation, that was the case. Okay, so we analytically also solved it. Okay, we can actually combine these two figures for expected return as a function of the weight of the stock and the portfolio standard deviation as a function of the weight of the stock, and just substitute out the weight of the stock so that you can see that what happens as you change the different weights, what are the different combinations of expected return and standard deviation that is possible. Again, in this graph, we have drawn these curves for different values of rho. So for rho equal to 1, you have basically got a line joining this D and E. And basically, as you are changing the weights that you are putting to the different assets, you are just moving along this line. Okay. Similarly, for rho equal to -1, these are the graphs. But for us, the numbers that were given, rho equal to 0.30, this is the curve that we have. Okay. So this is saying that as you are changing the weights of the stock and the equity, these are the different combinations of expected return and standard deviation of portfolio that are possible. So here we have drawn the graph, assuming that you are not allowed to do any shorting, so that you have got W lying between 0 and 1. So the question is, these are the feasible points that are possible from an investor's perspective in terms of expected return and standard deviation. The question is, which particular point along these points will the investor select, right? So again, we can think about it first generally, and then we can see analytically what will be the result. So the investor clearly wants to select the optimal portfolio from the opportunity set. So for the particular values that we have for rho equal to 0.30, these are the points that are there along the opportunity set, right? Now, what's the best portfolio? Well, that will depend on what the risk aversion of the investor is, right? So in general, clearly we can see that portfolios which are to the northeast, they have better because they have got higher expected return, right? And lower standard deviation. So you want to move as much to the northeast as possible. Of course, you are still subject to the constraint that you cannot move more northeast than this set of curve, for example, when you have got rho equal to 0.30. And ultimately, where you end up depends on your risk preference. But typically, we would expect that investors, those who have got greater risk aversion, they will prefer portfolios to the southwest, in the sense that they are okay with lower values of expected return because they are getting lower risk in the sense of lower standard deviation as well, right? Okay, so that is the general insight, but how can we make things a bit more concrete? So here we can actually solve also for what will be the weights for a particular investor. So suppose that the expected rate of return on the portfolio is given by this expression that you see here. So this is the same thing that you have seen before, except for the fact that we are substituting in that the weight of the equity is 1 minus WD, right? Apart from that, it's exactly the same thing that you have seen before. We can do the same for the variance of the return on the portfolio. So the same expression that you had seen before for the variance of the portfolio, except for the fact that again that we are substituting in WE is equal to 1 minus WD in this expression. And as before, investors are choosing WD to maximize their utility function, which is of the standard mean variance form. Okay, so what happens if we plug in the expected return and the variance of the portfolio? So this is again what we want to maximize. So first we plug in what's the expected return of the portfolio. So if you simplify this, this is nothing but this expression that you see here on top, okay, minus A times the expression that you see for the variance of the portfolio, right? So we are just plugging this in. Okay. The good thing is that if you make these substitutions, expectation of RD is a parameter, expectation of RE is a parameter, A is a parameter, sigma square D is a parameter, sigma square E is a parameter, and rho D is a parameter, right? So the only thing that one is changing is this WD, right? So again, this becomes an optimization problem involving one variable, and you can take the derivative with respect to U, set it equal to 0, and you end up basically getting a linear equation in WD, which you can solve and get an expression for W star D that you see here, right? So not as clean solution as the case that we had done for the case involving one risky asset and one risk-free asset. However, still the general procedure is the same, even though this time it was a bit more complicated in the sense of getting this expression for the variance, right, compared to the before. However, you can also again get the W star E by just looking at 1 minus W star D. So this, you can see that the general procedure is still the same. And our next step will actually be to combine the first two cases and think about a portfolio which has some risky assets as well as a risk-free asset.